What if the key to unlocking the universe's deepest secrets lies not in telescopes, but in ants? Can their tiny brains solve cosmic mysteries? Deep space, a realm dwarfing our comprehension, extends far beyond our solar system into a cosmic abyss that challenges the very limits of our understanding. The observable universe, a sphere stretching across 93 billion light-years, renders Earth a fleeting speck against an infinite canvas. What lies beyond this horizon? The question echoes, unanswered. What we perceive is merely a fraction of the cosmic narrative. Ordinary matter, the atoms and elements that constitute everything we know, comprises a mere 5% of the universe. The remaining 95% consists of dark matter and dark energy, enigmatic forces that shape the cosmos yet remain elusive. Consider the Boötes void, a region nearly 330 million light-years in diameter, an almost unimaginable emptiness containing only a handful of galaxies. How did such a void arise, and what secrets does it conceal? Even faint whispers from the deep ignite our imaginations, such as the wow signal, a brief, powerful radio burst detected in 1977, tantalizing us with the possibility of extraterrestrial communication. Yet, hope flickers brightly. The James Webb Space Telescope peers into the infrared, allowing us to glimpse galaxies from about 200 million years after the Big Bang and witness the birth of the earliest stars and galaxies over 13.5 billion years ago. We are looking back in time, striving to unravel the universe's genesis. The serendipitous discovery of the cosmic microwave background radiation in 1964, the afterglow of creation itself, provided compelling evidence supporting the Big Bang theory, forever changing our understanding of the universe's origins. Before we journey further, what mysteries do you think deep space holds? Subscribe to explore with us. Picture an ant colony, seemingly chaotic, yet achieving feats of breathtaking efficiency. These tiny insects hold a key, a blueprint whispered by nature itself, for unraveling some of the universe's most intricate puzzles and colony optimization, or ACO. Conceived by Marco Dorigo in the early 90s, ACO mirrors the ingenuity of ants, deciphering how collective intelligence blossoms from individual simplicity. At its heart lies the pheromone trail. As each ant forages, it leaves an invisible chemical signature, a pheromone, marking its path. Other ants instinctively follow this trail. The more ants that tread a path, the more potent the pheromone becomes, creating a self-reinforcing loop, nature's way of illuminating the most efficient route. Consider the double bridge experiment. Presented with two paths to food, ants initially make random choices. However, the shorter path leads to swifter pheromone reinforcement. Soon, the majority of ants converge upon the optimal route. Pheromone evaporation is also critical. Without it, the algorithm would become ensnared, settling on the first solution, even if suboptimal. Evaporation fosters exploration, enabling the discovery of new, superior paths, thwarting stagnation, and ensuring adaptability. The first ACO algorithm and system demonstrated that artificial ants could tackle complex problems, notably the traveling salesman problem. Since then, ACO has addressed challenges from optimizing vehicle routes to scheduling tasks and coloring graphs. Remarkably, some studies suggest that in certain scenarios, ACO algorithms may surpass even the most sophisticated optimization techniques, including genetic algorithms and simulated annealing, harnessing nature's inherent, potent problem-solving prowess. A power that might just unlock the secrets of deep space. But how can the seemingly simple behavior of ants unlock solutions to the complexities of deep space? The answer lies in optimization. ACO proves adept at tackling combinatorial optimization problems, scenarios where the challenge lies in identifying the best solution from a vast set of possibilities. Picture a spacecraft charting a course through the solar system, not a straight line, but a delicate dance with the gravitational forces of planets, moons, and the sun. Deep space trajectory optimization is a high-dimensional puzzle. Traditional methods often fall short, yielding routes that are far from ideal. The European Space Agency's Rosetta mission provides a compelling example. To reach Comet 67P at Churyumov-Gerasimenko, Rosetta embarked on a complex journey, leveraging gravity assists from Earth and Mars. Such maneuvers demand sophisticated optimization techniques. Imagine mapping out the most fuel-efficient route for a spacecraft visiting multiple destinations, a problem analogous to the traveling salesman problem. ACO algorithms have demonstrated real promise in solving these dilemmas, offering a pathway to more efficient and cost-effective space travel. Researchers at NASA's Jet Propulsion Laboratory are exploring bio-inspired algorithms, including ACO, for future deep space missions. The goal? To empower spacecraft with autonomous navigation and intelligent resource allocation, allowing them to venture further and explore more efficiently. This could revolutionize how we explore the cosmos. Decoding the cosmos demands sifting through mountains of data, where faint whispers of distant worlds often drown in noise. Telescopes like Kepler and TESS continuously scan the heavens, recording the light curves of countless stars. Within these light curves lie the secrets of exoplanets. But teasing out those secrets is a monumental challenge. Traditional methods of transit detection, which rely on identifying periodic dips in a star's light as a planet passes in front of it, frequently falter. Stellar activity, instrumental artifacts, and even the subtle pulsations of the star itself can mimic the telltale signs of a planet. This is where ACO enters the stage. Imagine ants foraging for food. They possess no map, yet they consistently find the shortest path. Their secret? Pheromones. ACO algorithms mirror this behavior. In the context of exoplanet detection, each ant represents a potential transit signal, characterized by a specific period, depth, and duration. The pheromone deposited by these virtual ants signifies the likelihood that a given set of parameters corresponds to a real planet. Countless simulated ant colonies explore the vast parameter space, searching for the strongest, most consistent signals. A 2016 study demonstrated the power of this approach. By applying ACO to Kepler data, researchers successfully identified exoplanet candidates with a higher success rate than some conventional methods, particularly excelling at detecting planets with weak transit signals. The Kepler 90 system, a star boasting 8 confirmed planets, became a prime target for ACO-based studies, showcasing the algorithm's ability to identify multiple planets orbiting a single star. Yet, the computational cost remains a significant hurdle. Simulating numerous ant colonies to thoroughly explore the parameter space demands considerable processing power. But researchers are developing parallel computing techniques to overcome this limitation and unlock the full potential of ACO. The future holds immense promise. As we prepare to analyze the data stream from the James Webb Space Telescope, ACO stands poised to play a crucial role, not only aiding in identifying new exoplanets, but also in characterizing their atmospheres, searching for biosignatures that might betray the presence of life beyond Earth. The cosmos speaks in many tongues: light, radio waves, and even the faint tremor of spacetime itself. These tremors, gravitational waves, were theorized by Einstein and finally detected in 2015. But these signals are incredibly faint, often lost in detector noise. ACO offers a surprisingly effective way to sift through this cosmic static. Imagine ants searching for food, leaving trails of pheromones. ACO algorithms mimic this behavior, treating the identification of gravitational wave signals as an optimization problem, searching for the most likely signal buried within the noise, strengthening the paths that lead to the most promising candidates. One key target is the chirp signal of merging black holes. This distinctive waveform can be meticulously extracted from noisy data using ACO, optimizing the parameters of matched filtering to significantly improve the precision of detection. A 2020 study demonstrated that ACO algorithms could enhance the detection rate of gravitational waves from binary black hole mergers, especially those weaker signals that might otherwise go unnoticed. The Virgo detector, working with LIGO, relies on noise reduction techniques, some inspired by ACO, to pinpoint the cosmic origins of these gravitational waves. This triangulation allows us to locate their source with increasing accuracy, peering into the heart of the most violent events in the cosmos. Researchers are exploring hybrid approaches, combining the strengths of ACO with other machine learning techniques, pushing the boundaries of sensitivity and accuracy in gravitational wave detection. By harnessing the collective intelligence of simulated ant colonies, we are unlocking new ways to listen to the universe, unveiling the secrets hidden within the faintest ripples of spacetime, and witnessing the universe's most dramatic events unfold. The immense gulf between stars poses a daunting challenge, charting a course that minimizes fuel consumption while maximizing scientific discovery. Traditional methods often falter when confronted with the intricate gravitational dance and the scale of interplanetary distances. But what if the answer lies not in complex equations, but in the behavior of ants? ACO provides a remarkably effective approach to spacecraft trajectory design. Picture a colony of ants searching for food, each leaving a trace of pheromones. The more ants that traverse a path, the stronger the pheromone trail becomes, drawing even more to follow. Gradually, the shortest, most efficient route emerges. ACO applies this principle to spacecraft routing. Here, ants become simulated probes, each exploring a range of trajectory options. Pheromones represent a blend of critical factors: fuel cost, travel time, and risk. The algorithm iteratively refines these routes, favoring those that promise the lowest overall cost. Studies suggest that ACO algorithms can reduce spacecraft fuel consumption compared to conventional methods. This translates into longer mission durations, greater payloads, and access to destinations once considered beyond our reach. Consider a mission to Europa. Researchers at NASA's Jet Propulsion Laboratory demonstrated ACO's potential by designing fuel-efficient trajectories for just such a mission, navigating the Jovian system's complex gravitational landscape, and pinpointing routes that minimized fuel expenditure while maximizing scientific observation. The European Space Agency has also been exploring ACO to optimize interplanetary transfer orbits, particularly for missions that leverage multiple gravity assists. One of ACO's core strengths is its ability to handle complex constraints. Planetary alignment windows, launch vehicle capabilities, communication blackout periods, all these factors can be seamlessly integrated into the algorithm, ensuring that the resulting trajectory is feasible and optimal. Simulations have even showcased ACO's talent for finding optimal routes through the asteroid belt's chaotic gravitational environment. Moreover, ACO possesses the ability to adapt to changing conditions mid-mission, dynamically adjusting the pheromone trails and recalculating the optimal route in real time. The application of ACO to spacecraft routing signifies a paradigm shift, a testament to the power of bio-inspired algorithms to conquer some of humanity's most daunting challenges, paving the way for a new era of deep space exploration. Imagine a scientist, hunched over a console, watching an algorithm subtly mimicking the foraging strategies of ants begin to paint a new, unexpected picture. This is emergent intelligence, a virtual ant colony charting a course no human mind could have conceived. Marco Dorigo's initial foray into optimization laid the groundwork for ACO. But its application to the cosmos remained a distant dream. The true leap forward came with Dr. Dario Izzo at the European Space Agency, who envisioned a grander potential interplanetary trajectory design, specifically for missions reliant on low-thrust propulsion. The scale of the problem was immense. Traditional methods faltered. Then, ACO was used in the trajectory design for Bepi Colombo, a mission to Mercury facing significant fuel constraints. As the algorithm ran, countless generations of simulated ants explored trillions of possible trajectories, each depositing a virtual pheromone trail. The strongest trails attracted more ants, reinforcing the optimal solution. The scientist watches as the virtual colony converges, an elegant and efficient trajectory emerging. Izzo's team tackled the grand tour problem, charting fuel-optimal routes to multiple planets with a single mission. ACO isn't just optimizing, it's innovating, uncovering solutions that human intuition cannot reach. The universe, it seems, speaks a language that even ants can understand. But even promising algorithms stumble. ACO is not immune to limitations. Its computational burden soars as complexity intensifies. Then lurks the danger of premature convergence. Moreover, the cosmos is a realm of perpetual change, challenging traditional ACO, which falters when faced with real-time shifts. ACO's performance is also delicately balanced on internal settings. To navigate these challenges, researchers are pioneering hybrid models, merging ACO with other potent optimization strategies. It's vital to acknowledge that ACO lacks the absolute assurances offered by some methods. While it often yields excellent results, there's no guarantee of pinpoint accuracy. And with the deluge of data from deep space probes, scalability remains a key obstacle. These are the cutting edges of current research, the trials that must be conquered to fully leverage ACO in unraveling the enigmas of deep space. The future of space exploration may well be written in the language of pheromones. As NASA's Deep Space Network strains under the demands of probes pushing further into the unknown, bio-inspired algorithms emerge as a solution. Imagine a sophisticated form of air traffic control for the cosmos, poised to boost efficiency. Consider the challenge of charting a course to Mars or Europa. ACO could pinpoint the most fuel-efficient trajectories, potentially shaving millions off mission costs. Studies have indicated fuel savings compared to conventional methods. These are game changers, reshaping the economics of space travel. Looking beyond individual missions, the European Space Agency is pioneering the use of swarm intelligence to manage satellite constellations, autonomously adapting to fluctuating conditions and optimizing data collection in real time. On Mars, in-situ resource utilization, or ISRU, is paramount. ACO could orchestrate the strategic placement of mining equipment and the extraction of water ice. And what of the impending data deluge from next-generation space telescopes? Bio-inspired algorithms offer a crucial lifeline, sifting through the noise, detecting anomalies, and pinpointing potentially habitable exoplanets. Finally, consider the threat of space debris. Swarms of autonomous robots, guided by ACO, could collect and deorbit defunct satellites. These bio-inspired approaches provide a robust and adaptable solution to the challenges of space exploration, particularly in the face of dynamic environments. It seems the humble ant may indeed hold a key to unlocking the universe. Behold the Boomerang Nebula, considered one of the coldest known objects in the universe of frigid -272 degrees Celsius, a breath away from absolute zero. Imagine gas ejected from a dying star at nearly 600,000 kilometers per hour birthing serene beauty. Now, picture ants finding the shortest path through a dense forest. These disparate images are interwoven by the mathematics of optimization. Algorithms, inspired by these navigators, now chart courses through the cosmos, minimizing fuel consumption and maximizing potential. But the connection resonates deeper. Consider the cosmic microwave background, the afterglow of creation, a seemingly uniform radiation, yet riddled with infinitesimal temperature fluctuations. These variations seeded the very structure of the universe. Envision the pillars of creation, actively birthing stars. Within the observable universe, galaxies ignite the darkness, each a universe unto itself. It is estimated that the combined mass of all ants on Earth mirrors the total mass of humanity. From the smallest creature to the grandest nebula, the universe whispers of interconnectedness. The ant's path, the spacecraft's trajectory, the galaxy's spiral arm, all dance to the same cosmic rhythm, a rhythm we are only beginning to comprehend, guided by the wisdom woven into the smallest among us. Ant colony optimization, a seemingly simple algorithm mimicking ant foraging, offers a powerful and surprisingly effective approach to tackling complex deep space problems like exoplanet detection, gravitational wave data analysis, and efficient spacecraft routing, potentially revolutionizing our understanding of the universe. Given the unexpected effectiveness of this approach, what other seemingly unlikely sources might hold the keys to unlocking the universe's deepest secrets? Let us know your thoughts in the comments below.